Welcome everyone, my name is Michael and today I'll be giving an introduction to machine learning. Specifically, my goal is to explain how to build a good enough intuition of machine learning to be able to apply it to your data analysis. To me, a zoo feels like an accurate description of the analysis methods used in my field, which is neuroscience. Every paper uses different machine learning methods, and it may seem like it would take a lifetime to learn them all. So how do you even start? First, let's define what we mean by machine learning. There are many definitions, but I like this one for its simplicity. The ability to automatically learn from data to identify patterns and make predictions. The diagram on the right presents the most commonly used classes of machine learning methods. For example, you know linear regression, right? Linear regression is a machine learning method because it identifies a pattern, namely a particular linear relationship, and can be used to predict y from x. Regression can also be nonlinear, and in general looks for a relationship between a continuous dependent variable y and an independent variable x. Classification is another class of machine learning methods. Here, you're also looking for a relationship between y and x, but now y is categorical rather than continuous. In the simplest case, the category is binary, either yes or no. In this example, every sample has two features, x1 and x2. And a classification boundary can be drawn such that samples in the top left correspond to yes and samples in the bottom right correspond to no. Dimensionality reduction is a class of machine learning methods which reduce the number of features in your data, in other words the dimensionality of x, while retaining as much important information as possible. For example, if you have two features x1 and x2, but most of the variance in the data can be captured by the axis denoted by PC1, then by calculating the position of each sample on this axis, you've effectively reduced the number of features to 1. Last but not least, clustering is a class of machine learning methods which look for clusters in your data such that points in the same cluster are most similar to each other. For example, in the below figure, all samples whose features are similar to each other form one of three distinct clusters. Regression and classification are supervised methods because they're taught to associate x with the correct y, in other words, the ground truth. On the other hand, dimensionality reduction and clustering are unsupervised because they're only trained on x. There is no ground truth. Machine learning methods have massively increased in popularity over the past 2 decades. Here, I use the dimensions.ai database to quantify the number of papers which contain the term machine learning or the term cross-validation, finding an over 50-fold increase in each one since 1990. In comparison, use of the term neuron only increased by about 6-fold, due to a general growth in the number of papers being published. Sadly, despite its immense importance, there are relatively few courses that teach machine learning end-to-end for a general scientific audience. In other words, focusing on breadth without going into theoretical depth. As a result, students are often left needing to teach themselves, but it can take a while to figure out how. I came up with the building blocks framework on the right to explain exactly what one needs to learn to apply machine learning to data analysis. So let's start with the first building block, programming language. As of 2024, Python is the most popular option for doing machine learning. It is popular due to the wealth of open source tools available, particularly for machine learning, and the ease of sharing and collaboration. MATLAB and R are also popular options. Don't fear the snake. If you haven't learned Python yet, there are countless free online resources for learning it, and I'm going to link some of those in the description. For those coming from MATLAB, the biggest difference is that Python has a lot less built in. It comes with neither the environment nor the needed libraries to do machine learning. All other differences between MATLAB and Python are mostly just syntax and can be learned in a few days if you're really dedicated, or a few weeks. The second building block is the environment in which you code. As I mentioned, Python does not come with a built-in environment. You therefore need to choose and separately download such an environment. The most popular environment for machine learning currently is Jupyter in Visual Studio Code. Now, Visual Studio Code, not to be confused with Visual Studio, a distinct product, is a free development environment by Microsoft. It is popular because of the countless extensions you can download that improve its functionality. Jupyter, also a standalone environment, is one such extension that allows Python programming in notebooks. This is useful for machine learning because notebooks allow you to create analysis pipelines, and machine learning applications are typically analysis pipelines. The third building block is concepts, and in my opinion this is the hardest building block to learn. The critical thing to understand is that you will rarely need to program a machine learning method from scratch, since nowadays all the commonly used methods are available in Python, MATLAB, or R libraries. That means you do not necessarily need to learn the theory and algorithms behind each method. However, you do need to learn the concepts behind each method, and I will illustrate why with an example. Say you got the data X on the right, and you want to identify the clusters in it. You look up Python clustering method and find you can use the k-means function from the scikit-learn library. So you run the following code. From sklearn.cluster import k-means, which imports the k-means function. Clusters equal k-means.fit x, which fits the clusters to your data, and labels equal clusters.labels, which extracts the labels from the fitted model. Then you plot the data again, but now you color code based on the cluster labels. Weird, you'd say. It splits my data into 8 clusters, but it looks like it should just be 3 or 4. This can't be right. The reason is that k-means has n clusters as one of its parameters with a default value of 8, and since you didn't specify it, then that's what the algorithm used. Had you learned the concept behind k-means first, you would know to separately look for the best n clusters, for example by calculating the silhouette score for each value. This will give you a clear peek at 3 clusters, corresponding to a much nicer clustering performance on the right. How do you go about learning concepts? For me, as a visual learner, this is what I do. Step 1, go to YouTube. Step 2, type the name of the concept and StatQuest in search. Watch the StatQuest video if there is one, probably at greater than 1x speed because these videos are quite slow. Step 3, if there is no StatQuest video or the concept is still not clear, shop around for other good videos. Here the video thumbnails are helpful. If someone put in the effort to create graphics for their tutorial, it's probably a good video. On the other hand, if they just scribble down some equations, maybe it isn't. But hey, you never know, so check it out anyway. Lastly, if the concept is still not clear, turn to Google, Wikipedia, or ChatGPT, a product of machine learning which is quite good at explaining machine learning concepts. In general, I would recommend learning machine learning concepts in this order. First, learn foundational machine learning concepts that apply widely across methods, including but not limited to cross-validation, bias-variance trade-off, regularization, mutual information, R-squared, and ROC-AUC. Second, learn the concepts behind the most common machine learning methods of each class. For regression, start by learning simple linear, multiple linear, Poisson, and logistic regressions. Classification, learn support vector machines, k-nearest neighbor, naive Bayes, and decision trees. For dimensionality reduction, learn PCA, ICA, and t-SNE. For clustering, learn k-means, hierarchical, and Gaussian mixture model clustering. Third, move on to learning more advanced methods which are currently at the edge of research in your specific field. For example, deep learning. Finally, you have all the needed software and sort of know what you're doing, but how do you actually do it? Here, it's often best to Google examples specific to your chosen machine learning method and try to modify them to fit your purposes. If programming in Python, you will find certain libraries are commonly used for machine learning, namely pandas to represent the data, scikit-learn for the machine learning methods themselves, and Seaborn to visualize the results. All these libraries come with the Anaconda distribution of Python, which I highly recommend downloading if you're doing machine learning. In the description, I will provide links to a few such method examples along with other useful free resources. Thanks everyone for listening, and a special thanks to Alon Rubin and Pritish Patel for their helpful suggestions. If you enjoyed this video, give it a like and share it with anyone else it might be useful to. Bye!